Good morning, good afternoon, good evening, everybody. This is Mr. Arocena, and on today's video, we're going to be talking about conjugate acids and bases. So the last video in this series, we discussed Bronsted-Lowry acids and bases, and then the one before that, we discussed Arrhenius acids and bases. So as a quick recap, the Arrhenius acids and bases, we'll just call those Arrhenius. So the Arrhenius acids and bases, they were defined by releasing hydrogen ions for an acid and releasing hydroxide ions as a base. And then the Bronsted-Lowry bases were defined as, Bronsted-Lowry acids and bases were defined as either donating hydrogen ions or as an acid, so this is an acid. And if they were a base, then they were accepting hydrogen ions. Sometimes we would call these proton donors. I think quite often they're called proton donors for acids, and then bases are quite often called proton acceptors because they accept protons or hydrogen ions. Because if you remember from the last video, we discussed what a hydrogen ion actually is. All right, so today we're going to discuss conjugate acids and bases. Now, what is a conjugate acid and a conjugate base? Quite simply, they're basically just two compounds that are basically the same. The only difference is that one compound has an extra hydrogen, or you can view it as one compound is lacking a hydrogen. Okay. So these always come in pairs. So an example of a conjugate acid base pair would be something like let's say H2CO3 and HCO3 minus, because they only differ by one hydrogen. The H2CO3 has two hydrogens, the HCO3 minus has one hydrogen. So that's how you can tell whether a pair of chemical compounds is a conjugate acid or base pair. Now, based on our definition of a Bronsted-Lowry acid, it makes sense to define the conjugate acid as the compound that has the extra proton. Because if we think of acids as proton donors or things that give away hydrogen ions, then anything that has an extra hydrogen or an extra proton is more likely to give it away. So therefore, it's most likely going to be the acid in that pair. And then similarly, the conjugate base is the compound that lacks the extra proton. Because if a compound lacks a hydrogen, it has a better ability to gain a hydrogen. Okay. It's not to say that some substances can act as one or the other depending on the situation. So for example, HCO3, depending on what it's paired up with, can actually be in a conjugate acid. So here in this pairing, this is the conjugate acid, and this is my conjugate base, because the HCO3 has the extra hydrogen, whereas the CO3 minus does not. But if I go back to my first example here, in this case, the HCO3 is a conjugate base because it has less hydrogens than the H2CO3. So this is my conjugate acid. So when you're looking at a pair of substances, the only thing you can use to tell them whether one is a conjugate acid or one is a conjugate base is consider which one has more hydrogens. The more hydrogens is going to be the conjugate acid. The less hydrogen one will be the one as the conjugate base. All right, now let's consider the next example. So here, this is the ammonia. This is the reverse of the ammonia reaction. This is ammonium. The ammonium ion, so this is ammonium ion. The ammonium ion reacting with water to create ammonia and H3O+. So what are the conjugate pairs? So in this first pairing here, the first pair, actually that's not the first pair. The first pair would actually be the NH4+ and NH3, though that's not actually a pairing, so that's not actually a pairing. And then the other pairing would be the H2O and H3O+. Okay, because when we're looking at conjugate bases and acids, we're looking for two substances that are very similar. They only differ in one hydrogen. Now, in each pairing, we're asked to identify what is the conjugate acid, what is the conjugate base. In the first pairing, the NH4 plus NH3, this would be the conjugate acid because it has the extra hydrogen. It has 4 hydrogens here. This would be the conjugate base because it lacks the extra hydrogen. No, it only has 3 hydrogens. Okay. With the water and H3O plus, this would be the conjugate base because it only has 2 hydrogens. And this would be the conjugate acid because it has 3 hydrogens. So identifying the conjugate pairs is really just look for 2 things that are basically the same. And then they only differ by 1 hydrogen. Okay. And the one with more hydrogens is the conjugate acid. The one with the less hydrogens is the conjugate base. Right. And anytime you do an acid-base reaction, you'll always end up with these pairings. You'll always have a conjugate acid-base pair somewhere in the reaction. Okay. All right. Now let's talk about organic acids and bases. Because these ones are a little harder to recognize than inorganic acids and bases. So an organic base, or sorry, an organic acid, we'll start with acids first. Simple organic acids end in this group here, the COOH. If you remember from organic chemistry, this is a carboxylic acid group. Carboxylic acid group. And the organic diagram would actually look like this. C double bonded to O, OH, and then this would bond to some other random compound. Okay, in this particular substance, the H that gets released is this hydrogen here. Okay, this hydrogen is kind of loosely bound to the oxygen here, but it's free to leave. So any kind of organic base, or sorry, keep mixing that up, any kind of organic acid reaction will result in the H from this group leaving. So here's an example. I think I showed this in our last video. Oh wait, this is not the same example. This is not acetic acid. This is propanoic acid. Yeah. Okay, so here, this hydrogen will split off to become that H+. Now the H+ has to be donated to something, so this reaction would actually end up being like this. So the C3CH2COOH would actually combine with some kind of base. Let's make it water. And this would create CH3CH2COO minus, and then the hydrogen would combine with the water to create hydronium, like so. Okay. Now here, you can also, again, identify what's the conjugate acid and what's the conjugate base. Because if I look here, if this is my acid, we'll call that my conjugate acid. Its conjugate base would be this one. There's the conjugate base. And then for water, this would be the conjugate base, and this would be its conjugate acid. Okay. Now bases, organic bases generally end in an NH2 or NH group. Okay, and this is the reason for this is because the nitrogen has a great ability to accept hydrogen ions. So in an NH2 group, the nitrogen will look like this. And then this will be attached, and the nitrogen will have a lone pair of electrons here. This lone pair of electrons has a relatively large negative charge density, so it has the ability to attract large amounts of positiveness to it, which in our case for acid-base chemistry would be like the hydrogen. And I think the NH group is very similar. So an NH group would look like this, but the nitrogen would then have 2 lone pairs, or something like that. NH group would probably contain not 2, because that violates the octet. There would most likely be a double bond here, but again, you still get the lone pair. All right, so the lone pair allows the nitrogen to attract hydrogens to it. So in this example here, here's a base. There's our NH2. the NH2 will attract one of the hydrogens from the water to create this, and then the hydroxide ion. Okay. And again, when we look at this, we can see, okay, looking at our pairings, we have this substance and this substance. With this pairing, this is my conjugate base, this is my conjugate acid, and then with the water, OH, this would be the conjugate acid, this would be the conjugate base. Okay. There we go. There are more complicated organic bases and organic acids. So these two examples of organic acids ending in COOH and organic bases ending in NH2 or NH. So these are simple organic acids and simple organic bases. There are much more complicated ones out there, but they basically operate on the same principle in that somewhere on the molecule there's a lone pair or some other large negative charge density, and then with the acids you have a hydrogen that is loosely bound to something on that molecule, and that's how they can give away their hydrogens or how they can accept hydrogens. So moving on, when we deal with acids and bases, we sometimes have to deal with acid-base equilibrium. Now, acid-base equilibrium generally happens whenever you have some kind of acid or some kind of base in a system. Okay. There's one exception to this though, and that's the fact that there's a certain group of acids and bases which we call strong acids and bases. These substances generally do not reach equilibrium. Okay. And that's partly because the nature of strong acids and bases is such that they will always give away hydrogens or they will always accept hydrogens. There's kind of no in between for them. Okay. Now, in your textbook, there should be a table of acids and bases right after the solubility table. So right after the KSP table, that's the acid-base strength table. Okay, and we'll talk about the strong acids and strong bases in a moment. Okay, now for things that are not strong acids or strong bases, they will reach an equilibrium. So for example, this is the hydrosulfuric acid and carbonate. So this is not a strong acid, it's actually a weak acid. We'll talk about that in a moment. When this combines with, say, a carbonate ion, they will create the hydrosulfuric acid will donate one of the hydrogens there to become this, and then the carbonate becomes that. So there's an equilibrium. Okay, notice that rather than having a single straightforward arrow, we have the equilibrium arrow. Okay, now going along with this example, we can see that we have a forward reaction. So we have a forward reaction, and then we also have a reverse reaction. In the forward reaction, it's easy to see that the H2S, the hydrosulfuric acid, acts as the acid in the forward reaction. Okay, because here you're going from H2S, and then you're becoming HS minus. So in the forward reaction, the H2S is the conjugate acid, and then the HS minus is its conjugate base. Now, in the reverse reaction, the opposite is true. So in the reverse reaction, the HS minus ends up acting as the base. So in the forward reaction, the H2S is the acid. In the reverse reaction, the HS minus acts as a base because it is going to be receiving from the HCO3 going backwards. Okay. And you can say a similar thing with the CO3 2 minus and the HCO3 minus, in that in the forward reaction, the CO3 2 minus is a base, and in the reverse reaction, the HCO3 minus is an acid. So be mindful of that, in that when you're dealing with acids and bases, depending on which reaction you're looking at, the substance can act as a base or as an acid. And again, just have to look, is my substance giving? So here it is giving a hydrogen, or is my substance getting a hydrogen or receiving a hydrogen or proton, I guess, depending on how I want to look at it. Okay. All right. So yeah, so there's sort of a quick lesson on conjugate acids and bases. We'll talk about strong acids and strong bases in the next video because they're much more interesting and not to be confused with dangerous acids or bases. We'll talk about that in the next video. All right, if you have your textbooks with you, then your assignment for today will be as follows. Okay. And again, if you have any questions, you know how to reach me.